Welcome back everyone. In this lecture, we will prove the simplicity of alternating groups when n is greater than or equal to 5. So, let us try to understand the small alternating groups. Okay. So, if you think about it, A1 is going to be trivial and similarly A2 is also trivial. Okay. So, now if you go to A3, so which is inside S3, okay. So, that is going to be isomorphic to Z modulo 3Z. So, this is also a simple group, okay. So, this is also a simple group. So, recall that a group is said to be simple if it does not have any proper non-trivial normal subgroup, okay. So, yeah, group G is said to be simple if it has no non-trivial proper normal subgroup. So, obviously, there are two trivial normal subgroups. One is a trivial group and the group G itself. Okay. So, if G is simple, then it should not have anything non-trivial and proper normal subgroup. So, Z modulo 3Z is a simple group, that is easy to see. Now, if we go to A4, so then what happens? So, A4 is sitting inside S4. So, we have already seen that so A4 has this Klein 4 group as a normal subgroup. So, which we denoted by capital V. So, I will leave it to you to check. So, this is exactly identity 1, 2, 3, 4, 1, 3, 2, 4 and 1, 4, 2, 3. So, this is a normal subgroup of A4. A simple argument is that, so note that all non-identity elements of this capital V, they are all having same cycle type. So, the cycle type of each element is actually 2, 2. So, this is the cycle type. So, in particularly, so they must be conjugate inside S4. Okay. So, now if you just think about it, you can easily prove that they must be conjugate even inside A4. Okay. And so they are the only like elements of S4 that are having this particular cycle type 2, 2. Okay. So, in particularly, so these elements are conjugate. Okay. So, in particularly, so this Klein 4 group must be normal subgroup inside S4. So, as a group, as a direct product of group, you can check that this V is isomorphic to Z modulo 2Z cross Z modulo 2Z. Okay, it is an abelian group because it is a group of order 4. So, we have already seen that any group of order 4 either must be cyclic, which is isomorphic to Z modulo 4Z, or isomorphic to Z modulo 2Z cross Z modulo 2Z. So, A4 is not simple, that is what this observation says. So, now what is about A5 onwards? So, that is a theorem. So, one can prove that AN is simple for all n greater than or equal to 5. Okay. So, this is actually somewhat very important result in first course of introduction to group theory. Okay. So, there are many steps involved in this proof. So, let us go through one by one. So, let me just first state all the steps actually. The step 1 is actually realizing that so there is a very important distinguished set of generators for AN. So, those are nothing but 3 cycles. So, if you take any element, okay. So, and this is true for any n greater than or equal to 3. For n greater than or equal to 3, so if you take any element of this AN, so that is actually a product of 3 cycles. Okay. So, all the 3 cycles lie in A n, and you can prove that any element of A n is a product of 3 cycles for n greater than or equal to 3. So, that is the first step. So, then as a second step you can actually realize that which is we already proved. So, this is the lemma that I proved in the earlier class. So, if n is greater than or equal to 5, so then you can say that two elements, so 2 3 cycles sigma and sigma dash or conjugate. Okay. So, then any two 3 cycles sigma and sigma, they are conjugate in A n. So, we know that sigma and sigma dash, if they have same cycle type, then they must be conjugate in S n. But now what we are saying, if you take 2 3 cycles, they must be conjugate even in A n. So, since they are conjugate in A n, so if you can prove that okay, if you start with a normal subgroup, okay, let us say again assume n is greater than or equal to 5 and H is a normal subgroup in A n, and assume that H contains a 3 cycle. So, then with this assumption one can immediately conclude that H must be A n. So, how one can conclude this? So, this comes from step 2 and step 3. So, first of all, step 2 says that any 2 3 cycles inside A n, they must be conjugate. Okay. So, now if you take if H contains 1 3 cycle, let us call it sigma. Okay. So, here is the proof. If sigma is inside H, which is a 3 cycle, so then what happens, tau sigma tau inverse must be in H for all tau in A n. So, this is because H is normal inside A n, as H is being normal inside A n. So, then from step 2, you see that all 3 cycles are in H. Okay. So, now from step 2, step 1, we see that H contains all 3 cycles in A n. Okay. And in particularly it contains the subgroup generated by that, which is A n. Okay. So, that proves H is equal to A n. So, in order to prove actually A n is simple for all n greater than or equal to 5. So, we need to prove only the step 4. Okay. So, what is step 4? So, step 4 is that okay, you just prove H contains 1 3 cycle if H is a non-trivial normal subgroup in A n. Okay. If n greater than or equal to 5 and H is let us say non-trivial normal subgroup in A n, so then we prove that H has a 3 cycle. So, now step 4 implies actually the simplicity of A n. Step 4 implies A n is simple for n greater than or equal to 5 using step 2, step 3. Okay. Because any non-trivial normal subgroup of A n contains a 3 cycle. Now, using step 3, if it contains a 3 cycle, then it must be A n. Okay. So, we need to check only 2 steps. So, one is step 1, that is any element of an is a product of 3 cycle, and we need to check step 4, which is the non-trivial step, that for n greater than or equal to 5, any non-trivial normal subgroup must contain 3 cycle. So, let us prove one by one. So, let us check step 2, sorry, step 1. So, it says any element of an must be a product of 3 cycle. Suppose sigma is comes from an. So, then we can write sigma as some product of transpositions. So, now note that this transpositions, number of transpositions that appear in sigma, that must be even. So, R must be congruent to 0 modulo 2, as sigma is an even permutation. So, now in particularly we can actually group them together, now tau 1, tau 2 you group them together and so on, then tau r minus 1, tau r you group them together. So, now if you can prove that the product of 2 transposition is nothing but product of 3 cycles, so then that proves that sigma is indeed product of 3 cycles. Okay. Each one of them is product of 3 cycle, okay, product of 3 cycles will imply that sigma is a product of 3 cycles. Okay, how to check product of 2 transposition is indeed product of 3 cycles. So, that is easy. For example, if they are not disjoint and share one element in common, then it must be of the form AB times BC. Then we already checked AB times BC must be exactly ABC. Okay. So, this case is done. Now, let us say they are actually disjoint, then it will be of the form AB times CD. If it is of the form AB times CD, then you can write it as ACB times ACD. Okay. So, this I will leave it as you to verify. So, there is another way to actually write the same thing. If it is disjoint, you write it as IJ and KL. That the product of Ij and Kl is actually you can write it as Ijk and Jkl. So, this is different from the one you see here. So, like I said, the product of these transpositions or product of these 3 cycles and all, they do not need to be unique. Okay. So, here is another way of writing. So, I leave it to you to check these two. So, now from this it is clear that any product of 2 transposition is nothing but is actually a product of some 3 cycles. So, maximum 1 or 2 are involved. So, now that proves step 1. So, any element of an is actually nothing but product of 3 cycles. So, now we will come to this step 4, which says if you are in n greater than or equal to 5 and H is a non-trivial normal subgroup, then it must contain 3 cycle. So, this is actually somewhat involved. So, let us go again step by step. So, we have to use all the results that we have already proved. Okay. So, here is the proof of step 4. So, you fix n greater than or equal to 5 and let H is non-trivial normal subgroup inside AN. Okay. So, we want to show that this contains a 3 cycle. So, if you think about it, okay, if you take this transposition inside Sn, is there any way to kind of identify the transposition? So, one can identify the transposition using its fixed points. Okay. So, if it is so transposition must be non-trivial. Okay. It at least permutes 2 elements Ij, let us say. All other indices are fixed. So, that means it has the maximum number of fixed points. Okay. It is a non-trivial element, non-identity element having maximum number of fixed points inside Sn. Similar characterization one can give for 3 cycles when you think it as an element of AN. you take a 3 cycle, so it just let's say permutes ijk, all other elements are fixed. That means all n minus 3 indices are fixed. So, it is non-trivial element in an that has maximum number of fixed points. So, that motivates us that if you want to prove H is equal to an, so then if you are looking for some 3 cycle inside H, so then it is actually makes sense to actually look for some element that has maximum number of fixed points. Okay. So, take sigma is a non-identity element of H that has maximum number of fixed points. In IN. Okay. So, now what we claim, this sigma must be 3 cycle. Okay. This is the claim. This sigma is indeed a 3 cycle. So, once we prove this, then we are done. So, whatever it is, sigma is an element of Sn. So, it can be written as product of disjoint cycles, and the disjoint cycles also must have some property because sigma comes from an. Okay. So, write sigma as product of disjoint cycles. So, this is the cyclic decomposition of sigma. So, then we need to prove that this R is exactly 1 and sigma 1 is actually cycle of length 3. Okay. So, the very first case, assume that all of them are transpositions. So, that can happen. Okay. So, case 1, assume that all of them, that is all sigma i's, are transpositions. Okay, they are all disjoint cycles, but it can happen that they are all transpositions. Okay. If R is even, then it can be just product of disjoint cycles, transpositions. So, now so we claim that, so this actually then this sigma cannot be satisfying this property. It cannot have maximum number of fixed points. So, for that purpose, what we do, we actually produce some new element inside H. So, how are we going to do? Okay. So, because this sigma is indeed come from an, so this R has to be at least 2. Okay. This R must be at least 2 once we assume that they are all transpositions. Okay. So, since this R is greater than or equal to 2, you write sigma 1 as some ij, sigma 2 as some kl. So, they are disjoint. Okay. They are disjoint cycles, disjoint cycles. So, now you have n is greater than or equal to 5. So, choose say S, okay, which is different from I, J, K, L. So, I can choose one S. Okay. So, now you can set this tau, which is a 3 cycle again, which is just KLS. So, this is an element of A. Okay. So, now note that the H is normal in AN and sigma is coming from H. Okay. Now, if you take tau sigma tau inverse, this is going to be in H. So, because tau is in AN. So, now what we can do, we can look at this particular element tau sigma tau inverse sigma inverse. So, this is in H and this is in H. So, the product is in H. So, this is going to be our new element omega. Okay. So, our claim this element omega, which is tau sigma tau inverse sigma inverse, this is an element of H which has more fixed points than sigma. Okay. So, let us try to verify. First of all, we need to verify omega is not identity. Okay. So, omega is not identity. So, why is that? Because look at what happens when you apply it on k, omega of k. So, what it does, omega of k is tau sigma, so let us write it properly, tau inverse sigma inverse of k. So, note that what is sigma? So, sigma is the product, okay. Sigma is sigma 1, sigma 2, etc., sigma r, where sigma 1 is ij, sigma 2 is kl, okay, and you have this tau which is kls. So, what is going to be sigma inverse of k? That is comes from the sigma 2 inverse of k, because sigma i's are all disjoint transpositions. So, that means this is going to be exactly L. So, tau sigma tau inverse of L. But what is tau inverse of L? Tau inverse of L is this k. So, this is tau sigma of k. But what is sigma of k? Sigma of k is going to be L again, because that is sigma 2 of k. So, this is going to be tau of L, but tau of L is nothing but S. So, this is going to be S. So, omega of k is nothing but S, but obviously by choice S is not equal to k. So, that means this omega does not fix k. So, that means omega cannot be identity. So, this forces that omega is not identity. So, we have verified omega is not identity. So, now let us see what happens to ij. So, we claim that omega of I is I and omega of j is j. Okay. So, let us compute. I will do only one computation. So, let us look at omega of I. Omega of I is going to be what? So, again let me write it here. So, sigma is ij, kl and so on, some sigma of r, and tau is kls. So, that is all matters for us, kls ij kl. Okay. So, now what is omega? Omega is nothing but tau sigma tau inverse sigma inverse applied on I. So, sigma inverse of I is going to be j. So, tau sigma inverse tau inverse of j. So, j is fixed under tau. So, it is going to be tau sigma j, but sigma of j is going to be I. So, tau of I, but I is fixed by tau. So, it is going to be I. So, omega of I is exactly I. Similarly, you can see that omega of j is equal to j as tau fixes j and I both. Okay. Tau of I is I, tau of j is j. So, that is all you use, and sigma just switches I and j. So, because of that you can see that omega of I and omega of j, they are fixed by I and j are fixed by omega. So, now you can observe the following. If A is actually some fixed point of sigma, and if A is not equal to S, so then it is immediate that omega of A must be A. Why? Because again recall what is tau? Tau is nothing but KLS. Okay. So, anything apart from this KLS, everything else is fixed. So, now what is sigma? Sigma is Ij, KL and so on, sigma of r. Okay, that is your sigma. So, definitely I and j are not fixed point of sigma, KL they are not fixed point of sigma. So, if sigma of A is A, would immediately imply A is not equal to I, J, K, L. So, the only letter that remains is this S. This sigma, this A can be S. Okay. So, but if you assume A is also not S, then that forces that tau of A equal to A and sigma of A equal to A. So, both are true. If tau fixes A, sigma fixes A, then omega is nothing but what? Omega is nothing but tau sigma tau inverse sigma inverse. So, that means So, product of elements which are fixing A. So, omega fixes A. So, now you have how many elements? So, apart from this 4, okay, including this A, okay, you can see that except these 5 elements, all other elements are fixed by omega. So, now we also see that this I and j, they are also fixed by omega. Now, if you take this sigma except S, okay, everything else that fixes by sigma fixed by omega. So, that means the number of fixed points of omega is going to be exactly at least one more than, okay, number of fixed points of sigma plus 1. So, here we could possibly miss 1, sigma of S can be S, okay, but we do not care because all other elements are fixed by sigma or fixed by omega, and more than that I and j, they are also actually fixed by omega. So, you have removed 1 and added 2. So, that is why you get at least the number of fixed points of sigma plus 1, which is absurd because we assume that sigma has the maximum number of fixed points. So, that proves that this this sigma cannot be product of transpositions. Okay. So, this condition is actually not true. So, now once we proved this, then what is the case 2? So, then at least one of them should be having length greater than or equal to 3. So, let us assume because sigma is commute, we can assume sigma 1 has length at least 3. So, let us say sigma 1 is a cycle of length at least 3. Okay. So, now if r equal to 1 and sigma equal to sigma of 1, okay, and sigma 1 has length 3. So, then we are done. Okay. So, in this case we are done, or otherwise what can happen. So, sigma 1 can have length more than 3. Okay. So, there are two possibilities, either r is greater than or equal to 2 or length of sigma 1 should be more than 3. Okay. R is 1 and length of sigma 1 is at least 4, but it cannot be 4. If it is 4, then it becomes odd permutation. So, it has to be at least 5. So, only these two conditions can happen, but in both conditions you can see that sigma must move at least 2 elements, let us say P and Q. Okay. So, this implies sigma must move at least 2 more elements. Okay. So, now write sigma 1, again it is just some I, j, k and so on, it could be any length. Okay. This P Q is not coming from this I, j, k. Okay. Either it can be part of sigma 1 or it can be part of different cycle, but anyway whatever it is. So, now what you do, you construct again another tau which is k p q, take this 3 cycle k p q. As before you can construct this omega which is tau sigma tau inverse sigma inverse. So, which is going to be element of H because tau is element of A n. So, the conjugate, this is element of H and the product is element of H. So, now I will leave it you to check the following. Okay. This omega is actually not identity. So, especially what it does, omega of k is going to be P. Okay. So, it cannot be identity. So, now you can check that this tau sigma tau inverse sigma inverse, this actually fixes J. okay, and that is easy because this tau fixes j and sigma inverse actually takes j to I, okay, and I is also fixed by tau and sigma of I will become j, okay. So, note that sigma of I is j and sigma inverse of j is I, and tau fixes both I and j. So, using this you can verify that tau sigma tau inverse fixes j. And moreover, if you take tau sigma tau inverse, this fixes every element of this in that are fixed by sigma, okay. So, that is again not that hard to see because once sigma fixes some a, then sigma inverse of a will be a, but that tau inverse must fix that a because the way we constructed tau. Tau is the cycle k p q and p q I j k, they are not fixed points of this sigma, okay. So, this is also obvious. So, in particularly this omega has more fixed points than sigma. So, which is a contradiction. This is a contradiction to our assumption. Our assumption is this: either r is greater than or equal to 2 or r equal to 1 and the length of sigma 1 is greater than or equal to 5. So, both cannot happen. That forces that r is equal to 1 and the length of sigma 1 equal to 3 and sigma must be equal to sigma of 1, okay. So, this proves that this H must contain at least one 3 cycle, and from our earlier steps you can conclude that H must contain all 3 cycles. So, that proves that actually A n must be simple for all n greater than or equal to 5. So, this is a very important result that you learn in first course in group theory. Okay. Now, using this you can easily conclude something about the symmetric group. Okay. I will leave it as exercise, you can actually think about it. If you take Sn for n greater than or equal to 5, then you can actually prove that An is the only normal subgroup. Only normal subgroup of Sn. Okay. Okay. So, I will stop here and then like we will continue with other examples in the next class. Okay. Thank you.